Through the discussion in last lecture, we understand that the net magnetic dipole moment of an atom is key to understand magnetic materials. Before discussing the magnetic materials, let's recall the potential energy U of a system of a magnetic dipole moment. The potential energy of a system of a magnetic dipole in the field depends on the orientation of the dipole in the magnetic field. U equals minus mu dot B. When mu is parallel to the field, the potential energy is minimum, while it reaches maximal value when mu is antiparallel to the field. Therefore, when a magnetic dipole is placed in the field, the dipole will tend to align with the direction of the field due to the action of the net torque, so that the system has a minimum value of the potential energy. Now let me introduce a very useful vector quantity here, magnetization, denoted by a uppercase M. Magnetic materials consist of many permanent or induced magnetic dipoles. How about the average magnetic field produced by these magnetic dipoles all allied? It's a key point to understand the magnetic properties of materials. Let me give you a detailed analysis about it. As shown in the figure, we have a cylindrical material with a cross-sectional area A and height L. It consists of n magnetic dipoles, each with a magnetic dipole moment, mu. These dipoles are distributed uniformly over the volume. It's assumed that all the magnetic dipole moments are aligned with the axis of the cylinder. Now, let's compute the magnetic field produced by all these aligned dipoles. First, we define the magnetization vector M to be the total magnetic dipole moment vector per unit volume as expressed by this equation, where V is the volume of the material, that is A times L. In this case, all dipoles are aligned, so the magnitude of M is n mu divided by Al. We notice that in the interior of material, a current is always cancelled by another current in the neighboring loop with opposite directions. Only near the edge of the cylinder, this cancellation never occurs because no adjacent loop nearby. As a result, we have zero net current in the interior of the cylinder, while a net current appears on the side of the cylinder. You may look at this figure showing the top view, and this is the equivalent current on the edge of the cylinder, as denoted by IEQ. Based on the definition of the magnetic dipole moment, the moment associated with this equivalent current IEQ should be the total dipole moment in the cylinder. Hence, we have this expression, IEQ times A equals n times mu. So, the magnetic field produced by these aligned dipoles should be the field due to this equivalent current. We define a quantity, surface current, meaning current per unit length, which is denoted by a uppercase K. K equals IEQ divided by L. We found K just equal to M, considering IEQ equals to n mu over A. Please look at this figure. We note that the current configuration in this case is highly similar to a solenoid carrying a current IEQ. According to the magnetic field of a solenoid, B equals mu0 Ni, where Ni is just the current per unit length. So we have this one, B equals mu0 M. Since the direction of this magnetic field is in the same direction as the magnetization vector M, the above expression could be written in the vector form as this one. This is the average field due to all aligned dipoles in the material. Keeping in mind the result from our discussion above, we are going to discuss the magnetic properties of materials in the next lecture.